all we're going to be doing today is we're going to be determining whether it's likely that a sample comes from a normal population or not, right? We just examined the sampling distribution, right? This idea that if we fix n, the number of individuals we're going to randomly sample, if we repeatedly take random samples and we find the sample mean, the distribution of that mean, of that sample mean, will be approximately normal, assuming either that we're sampling from a normal population or that the sample is large enough. All right? So one thing that we can do is we can say, well, are we sampling from a normal population or not? That will help us sort of in our studies. Now, before we assess for normality of a population based on a sample, a couple things to keep in mind. No distribution is perfectly normal. That's not a thing in real life. So we're assessing only for approximate normality. When we're doing this process, we're trying to see whether a sample comes from a normal population. We're concerned primarily with small samples because the central limit theorem states that large samples, which is to say samples of size greater than 30, have an approximately normal, normal sampling distribution, right? Again, if we have a large enough sample, we can guarantee the sampling distribution, that sample mean, is normal, right? So the concern is, what about for small samples, right? What we're going to be doing here is we're going to be developing an intuition rather than strict formulas. Right. There will be one minor little mathematical thing we're going to check with QQ plots at the very end, but even then, it's very, very basic. So here are our criteria for assessing normality. If a sample contains any of the following, one or more of the following, then it likely does not come from a normal population. The population likely is not normal. If the sample contains an outlier, if the sample is heavily skewed, if the sample is not unimodal, i.e. has multiple modes, right? So, we understand what an outlier is, right? It's an extreme value in either the high or low direction. The sample is heavily skewed, right? It's got a big tail to the left or the right. And of course, if it's not unimodal, right? If it's got multiple modes, something like that. Right? Maybe bimodal, trimodal, etc. If a sample has none of these characteristics, then we assume its population is approximately normally distributed. So we're just going to look at a bunch of different graphs. What we're going to do is we're going to take a sample. We're going to look at the graph of that sample and determine whether the sample satisfies any of the properties in fact 1 through 3. If so, then the sample probably doesn't come from a normal population. If it satisfies none of them, then it probably does. So let's see, we're going to look at dot plots. I think the next one we look at is histograms. We're going to look at stem plots or stem and leaf plots. And then last but not least, we're going to look at box plots. And then we're going to look at another kind of plot after all this that we haven't seen before. But don't worry, it's not that bad. Called a QQ plot. All right, so for each of them, I'm just going to rip a bunch of questions in the book because that's really all we're doing is examples. Right, determine whether it's reasonable to treat the sample as coming from an approximately normal population. Yeah, this guy is an outlier. So we'll say since the sample contains an outlier, let's not say likely or unlikely. I should say it comes from a non-normal population. Okay. Now compare that to this guy over here. Are there any outliers? No. Right, and again, we're just kind of eyeballing this stuff, right? There's no formula or anything, right? We can just tell there's no outliers. Is there any skewness? No. Is there really bimodality or anything like that? No. So we'll say there are no outliers. There's no skewness. And what is it? The sample is unimodal. So the sample is from an approximately normal population. Okay, that's all we're doing. That's all we're saying. I guess I didn't even need to leave all this space, right? But that's what we're doing. So look at the following histograms, right? Maybe pause the video real quick. See whether these are from a normal population. We have, I even left a little bit of space. Probably didn't even need to do that. Oh well. Kind of just gonna do one of these guys. If you don't mind, a little bit of copy paste never hurt anyone, right? Because there's no outliers, skewness, bimodality. I'm sure someone's saying, "Oh, look, it dips a little bit." No. That's gonna happen most times. Like, it's never gonna be perfectly unimodal most of the time. This is effectively unimodal. Okay, so don't get hung up on this. This is legit. So the population is probably normal, right? This, on the other hand, that's some bimodality going on. So that population is likely not normal. Let me actually just sort of since the sample data is bimodal, its population likely is not normal, which means normally distributed, right? And that kind of makes sense, right? If you sampled a bunch of men and women and you notice that, you measured their heights and you say, this is bimodal data, it'd be reasonable to think, okay, maybe this is a bimodal population going on here with regards to height. Okay. So let's consider this stem and leaf plot right here, a stem plot. Is this approximately normal? Well, one thing you can do is you can turn your paper sideways so that the 1, 2, 3, 4, etc. is on the bottom. And the data is kind of sticking up like a histogram or a dot plot. And you just notice the shape is kind of a little taily, right? If you turn that graph, right? Just the basic gist. Kind of up and then it tails, right? That's skew. Maybe we'll use a highlighter. Right? That's skewness, right? So since the sample data is skewed to the right, its population is not normal. Okay. Now, let's see what happens here with box plots. Reasonable to assume that this population is approximately normal. Yeah. Yes, it is. Right? I don't want anyone saying, look, this whisker is a little bit longer than this, but no, they're basically the same. The median is basically in the middle of the box. There are no outliers. This is approximately normal. Now, the one thing that you need to be a little careful of with box plots is you don't really know anything about modality, actually. You don't know whether it's bimodal. So actually, maybe we should go ahead, maybe I should say, yeah, let's get rid of this. And there are no skewness, right? Box plots are not quite as helpful for detecting normality because we don't know about modality. But we work with what we've got. And based on this, there's no reason to think that the population is not normal. Okay. Now, the last thing that we're going to do, we're going to look at another measurement called Q. Well, okay, so I think the book calls them quartile plots. I've also seen them called QQ plots. And I believe that's what Dr. Teller and I like to use. In fact, I know it because that's what I use. So we're going to say QQ plots, okay? Okay, but again, if you're doing a book problem, it might say quartile, okay? And they actually use p-values to tell us, or actually, maybe you shouldn't even say p-values. That's a little much because we don't know that. They use z-scores, I should really say. That's what they do. Z-scores and then p-values, right? Same sort of thing. All you're going to do, you're going to get, if you get a graph, there's a very easy way to tell. But in the case that you need to create a graph, what you do, you take the data, enter it into Minitab, like I did. And then you just go to, you want to see whether it's approximately normal, you go to graph, probability plot, simple. Make sure to get that data in the y variable. Make sure distribution is set at normal. Yeah, I think we're fine. And then, oh, what the? I don't know why it's giving us both those lines. Hold on one sec. Sorry, I don't know why it gave us those extra lines. We did not need that. Let's try that. Nope, we didn't want that either. That was worse. Okay, so we're gonna do this. Let's try this. See if this is any better. No, that's not what we want either. Okay, so I guess we're gonna keep it the first way. I just don't like those other lines. Oh well, I guess that's what we've got. Ignore the little curves, and just look at the red line in the middle there. So all we're doing is we're taking a look. Let me just. There we go. So all we're doing is we're just looking to see, do those blue points stay roughly on that middle red line? Right? And the answer is, yeah. It's not perfect, but they're basically linear. Right? They're basically linear. So, yeah. If we go back over here, I'm just going to paste this somewhere. Okay, and what we're looking for is the following. We open Minitab, again, go to Graphs, Probability Plot. Didn't used to give those other lines. That must have been an update. Whatever. Anyway, we choose Simple. Enter your data column where appropriate. If the points roughly follow the line, now this is what the book says, and this is what I've seen before, but the kind of the basic standards is if points roughly following the lines means if p-value is greater than 0.5, then the population is approximately normal. If not, then the population is not normal. Okay. So again, you just kind of look at this p-value right here. right there. See how it's above 5? So that means that these points are close enough to the line that we're good. Okay. That's it. That's the whole thing. Now, I will just say that sometimes we give you problems from the book like this, right? Because the book doesn't have p-values. It's very clear that these points are not, let me get the highlighter out, very clearly not on the line at all, right? These guys are not normal, okay? That's all I've got.